In this video, I want to show you how to conduct one-way ANOVA test in R. Here are the steps to follow. Step 1. Estimate the descriptive summary of the variables. This is optional. 2. Test for the normality of the residuals. 3. Test for variance homogeneity. 4. Conduct the one-way ANOVA test. 5. Conduct the post-hoc test. So we only conduct the post-hoc test if the one-way ANOVA test is significant, if the result is significant. Then lastly, interpret, that is the effect size, if the test is significant. Okay, ordinarily when you conduct one-way ANOVA test in R, so the result will come with the effect size test. So we are going to interpret it only if the test is significant. Okay, take note of that. So the non-hypothesis we have before us that we want to test is this: there is no significant difference in stress scores across education levels. And alternatively, we can also restate that hypothesis in an alternative way, that is, education levels do not have significant effect on stress scores. And the data set we want to use is named stress score. Okay, so I've already set my working directory, so I will be importing my data sets. Let me import my data set by running a code here. Okay, so this data set has been imported. I can view the data set by running the line of code in line 22. So this is the line of code. So we have 3 education level. We have university students, then we have A-level students, then we have general population. So now let's go back to our script. So for convenience sake, let me attach the data set. So as usual, I'm going to use the function attach. Then I put the name of data frame in that as the argument. Then I run that. So the required packages I'm going to use, these are 3 packages we have been using. Then I run this. I want to load the packages. So let me highlight all of them at the same time. So I've already loaded them. So now the first step, I want to show the descriptive summaries of the variables. Okay, so as usual, I'm going to use describe by, because I want descriptive statistics to be by group. So I'm going to run that. That's line 34. If I run this line 34, I have this for each of the groups. For A level, I have descriptive statistics. For general population, I have descriptive statistics, and for university student, I have descriptive statistics. You can see the main for A level, that of general population, and that of university level. These are the mains we are comparing. You can see from here, you can see that the main stress score of university student is higher than that of general population, while that of university student is higher than A-level students. Okay, A-level students. You can see standard deviation. Okay, standard deviation. You can compare standard deviation. Okay, you can see that the none of the standard deviation is more than twice the other. Okay, it's more than twice the other. Okay, if I'm using the rule of thumb of variance homogeneity, I can assume that the variances are equal. We are still going to test that anyway. So I also have the minimum values and the maximum value. I have the kurtosis and skewness and so on and so forth. Okay, now you might be interested in checking if there are outliers. So we use the we use the box plots for that. So we have, you can plot your box plot by running the line of code in line 37. You can see we have box plot function. So we have stress score. We are going to run the stress scores. You can see that the variable stress score here. So we are running it on educational level. So on educational level, then the main, that's the title we want to give our chart. So let me run that. So you can see the box plot. Look at the box plot. If you look at the box plot, you can see that only at in A level student we have an outlier one. Okay, there's not that far, but there's an outlier there. Okay, so if you look at the spread, you can see that they are similar. The spread are similar, so you can get the idea of whether the variances are equal. Yeah, so they are somehow equal. Well, actually, that is not the purpose of using this box plot, but in fact that from here, so no outlier in university level score, general population score, but there's one outlier in A level student score. Anyway, so now the next step is to check for the normality of the residuals. How are we going to do that? So first thing we are going to do is that we are going to run a regression, okay, using LM function. It's an R-based function. We are going to run LM. We are going to run a regression model using LM function. So we assign this is LM function. Then we are going to run stress score. That's the variable. The dependent variable we are running on the grouping variable, that is the edu level. Then we are assigning this results to LM model. Okay, so let me run that. Then I want to extract the residuals of this model. This model has been run, so I want to extract the residual. What am I going to do? I'm going to type LM model, not model, LM model. That is, I'm going to use the exact name. So let me put it there. Okay, better still, let me rewrite. Okay, LM model. So I'm going to extract it by adding, I put in what's it called, $. I write residuals. So residuals, I'm going to extract that and assign it to resid. So what this one will do for me is to extract the residuals from these results, only the residuals, so that I'll be able to test to check if there's if the residuals are normally distributed. So let me extract that anyway. Yes, residuals have been extracted. So the next thing is to check for the normality of the residuals. The first thing I want to use Kiki plot. Okay. Now, as usual, we use GG Kiki plot. You can see that I put resid in the argument as the argument. So I run that. When I run that, I'm going to have my Kiki plot. You can see this Kiki plot shows that residuals are normally distributed. You can see very close to the line. Okay, so very close to the line. So now I can also use the format test to check that. So the format test, I'm going to use Shapiro test. Then as the argument, I'm going to put the residual there. So now let me run the residual. You can see the p-value for. You can see that the p-value for the Shapiro weak test is greater than 0.05. So we cannot reject the non-hypothesis of normality. That's normal distribution. So we assume that the residuals are normally distributed. So that assumption of normality of the residuals has been satisfied. So the next assumption we are going to check is the variance homogeneity. That's whether our variances are equal. Although earlier we have been able to check merely looking at our standard deviation by comparing our standard deviation with that one. Okay, if none of the standard deviation is more than twice any of the other one, so we assume that variances are equal. In this case, none of the standard deviation, okay, standard deviation of none of the group is more than twice the other. So we can assume variance homogeneity. But this is just a rule of thumb. But let's see how that is going to behave if we carry out our Levin test. Levin test is a test that is used to check for variance homogeneity, okay, across groups. So now let's check. Okay, so as usual, the argument, the first one is going to be the name of the data set. Then we have stress score. The next argument is going to be stress scores, not gender. Anyway, okay, that's a typo error. Gender, maybe it's gender. Okay, so then we are running it on education level. So if I run that, I'm going to have my result. You can see that the p-value here is greater than 0.05. I cannot reject the non-hypothesis of variance homogeneity. So we conclude that variances are equal. So when we use the rule of thumb, we arrive at the same conclusion. Now, this formal test is now confirming that. Now, having satisfied both assumptions, we can now proceed to conduct our one-way ANOVA test by using ANOVA underscore test function that is available in half statics package. So the first argument that this function is going to take is the name of the data set. Then we are going to run the dependent variable, that is stress score on education level. You can see we are running stress score on the education variable. So that's edu level. Then comma, we want to have our effect size, because if you put ordinarily, if you don't put this, the default effect size that comes with our result is eta squared. So it's going to come, because generalized eta squared is going to come with it. But in case we want partial eta squared, so we have to put this effect dot size, we set it to PES. So as we are going to see how it works when we conduct a two-way ANOVA test. Anyway, so in the meantime, so we set this to GES, because that is what we are going to use. This generalized eta square is the most appropriate for ANOVA test. So we are using this. So now, especially one-way ANOVA test. So let me run the test. You can see this is the test. Look at the p-value. We are interested in the p-value. This is the F statistics, and this is the p-value. You can see degree of freedom. Okay, 275. You can see this is it. You can see this is less than, this p-value is less than 0.05. So we are going to reject the non-hypothesis that we set earlier, that education levels do not have significant effects on stress scores. In other words, that is, there is no significant difference in stress scores across education level. So we are rejecting this non-hypothesis, and we are going to conclude that there is significant difference in stress scores across education level. That is, education levels have significant effect on stress scores. So that is what is going to be our conclusion. Now, this effect size is this size. We said it has effect on. We said that education level has effect. That education levels have effect on stress scores. So that effect we said is what is the size of that effect? That is what the practical significance of that effect. So we are going to check this generalized eta square. So this is the guideline to interpret. This is the guideline to interpret light. You can see this one is light. This effect, that is the effect that education level have on stress score is large. That's what it means. That's what it means. So having found a significant result, okay, so we can then proceed to carry out our post hoc test. So we are going to use two variants of test. We are going to use Turkey HSD test. Okay, so we are using Turkey HSD test first. So that we are going to use the function Turkey underscore HSD available in half statics package. And the first argument is going to be the name of the data set. Then we are running the dependent variable on the grouping variable. Then let's run that. Let's run our result. You can see we have our result here. You can see we have our result here. So what's our result? We have for A level, you can see for A level here and general population, there's no significance. Okay. What we are doing here is that we are comparing. We have found that the stress scores are different across education level, but we are trying to look at the groups that are responsible, that levels that are responsible for this difference we are talking about. Okay, you can see that the first one, look at the first one is A-level students and general population. Okay, no significant difference. Okay, so in their stress scores, look at these A-level student and university students. So there's a significant difference in their stress score. Okay, look at, and lastly, general population and university students also have significant difference in their stress score, meaning that it is these two levels that are responsible for the signal difference we observe here. That's what it means. Observe here. So let's also use Bonferroni test. This is highly recommended. Okay, so we prefer this Bonferroni test to Turkey HSD test. Okay, but this Bonferroni are just for inflation. So okay, now let me run Bonferroni test. You can see the function I'm going to use pairwise underscore t underscore test. Then the first argument will be the name of data set. Then we run stress score on education level. Then we have pool.sd. So meaning that here our variances are equal. If we have homogeneity of variances, so we are going to put this as true. Otherwise, we put false there. Then we are going to p.adjusted.method. We are going to put Bonferroni there. Now let's run that. You can see we got the same result. Okay, the same result we got when we use Turkey SD test. Not the same result per se, but the same conclusion. Okay, I wanted to say the same conclusion. Okay, the same conclusion, not the same result but the same conclusion. You can see, look at this. You can see the first comparison, that is A-level students and year population. No significant difference in their stress score. Okay, but between A-level students and university students stress score, there's significant difference. Okay, that is one of the levels that respond for the significant difference we witness in our general test. Then general population and university students, we have significant difference. You can see here in these two levels we have our differences lies. You can see this lies. That is the essence. So, and lastly, having found a significant difference, okay, so we having found where these differences lie, so we can carry out our OND test in order to check for the effect, the size of the effect. So now coherence underscore d, then we have the first argument in of data set, then we are going to run stress score on education level. Then we are going to var.equal that to show that the variances are equal. So we run that. We are going to have our result. You can see these are the effect size. These are the effect size. Okay, how large are they and how small are they? You can see for the first one, no significant difference. Just like we got that before. You can see here, no significant difference. So we do not expect any effects before. Okay, you can see this one. We are told that the effect size is 0.422. This is small. Okay, although it's of no use because it's not significant. We don't care about that. But for the last two levels, okay, that's A level student and university student, the effect size is 2.43. Okay, that is large. You can see the magnitude, that is large. And for the difference in the stress score between A level student, between university student and general population, the effect size is 3.34. So we ignore the negative when we are interpreting. It's also large. You can see it's also large. So here we stop because this is the end of the analysis.